hour for the lecture. So it's my great pleasure to introduce our seminar speaker for the Center for AI in Society today, David Shmoys. He's a professor at Cornell University in Operations Research and Industrial Engineering, as well as computer science. I have known David since the early years of my PhD. He was on my committee and also a collaborator and a great mentor. So I'm extremely happy to visit us today. David is also the director of the Center for Data Science for Enterprise and Society at Cornell. He works on the design and analysis of algorithms for discrete optimization, in particular NP-hard problems, and has worked in applying these in the fields of computational biology, inventory management, network design, scheduling, and also lately in the design of algorithms for the sharing economy, right? And so David's work has been phenomenal and has been recognized by many prizes. I'm going to skip a few, but the Informs Optimization Society Gatchen Prize, the Informs Lecture, Morse Lectureship, the Informs Kimball Medal, the Informs Wagner Prize, and the Informs Lanchester Prize. So we are really, really honored to have David today, and thank you for sharing your latest work with us.
To be here today and to talk to you about what is really ongoing work in developing an optimization toolkit and framework to think about a fundamental political problem, that of creating legislative districts in a very endemic and very, particular to US context. And indeed, the question will be how we can do this in terms of using our ability to do analysis from the models we build to understand various metrics of fairness as well. Oops, no, that did work. Okay, we're going to be overreacting, maybe? Okay, so the setting for the problem is embedded in the US Constitution. That at the highest level, every 10 years, the US conducts a census, and that, in addition to allocating the number of representatives that each state gets, means that each state is empowered, and it is indeed at the state level, to determine the districts for that state, both for the federal level, for the Congress, at the House of Representatives, and for the state legislative bodies as well, typically called the Assembly and the State Senate. And this means that every 10 years, all of these boundaries have to be redrawn. Furthermore, in this litigious society, once they've been redrawn and drawn, they get fought over in court. I'm from New York, and it's only a few years after 2021, and we're on our 4th map in terms of the congressional districts already, and who knows how long that'll last. So this is something that is very much fundamental to the core of the US democratic system. And there's one other piece that I want to highlight here, is that Congress also has the power to set new rules universally across the 50 states. So in fact, although each legislature makes up its own guidance, that the US Congress can also provide something that is relevant across all 50 states. And we'll come to a reason why that's relevant later. So at its fundamental core, this is an algorithmic problem, and I'm going to think about algorithmic solutions. I'm going to give you a whirlwind tour of actually 3 papers, one very much ongoing. But before you get too hung up on the fact that I'm talking about algorithmic solutions, what I'm interested in, and my perspective is very much, I want to build a toolkit that policymakers can use to help them make better decisions. I'm not talking about an algorithmic solution that, cover your eyes, there and out comes the answer. This is really a question of being able to navigate a solution space that is rich and complex, and to have tools to actually provide analysis and perspectives on the solutions that we get. So I'm an optimization guy, as Beaster just said. The core technology that has evolved more than any other over the last 50 years is that of integer programming. When I was a student as an undergraduate, integer programming was out there, but you didn't think about wanting to actually do real world scale integer programs. Well, okay, maybe you solve the linear programming relaxation and interpreted it and rounded it in a way. But today, integer programming is an off-the-shelf, viable tool that can solve all kinds of problems at scale in a way that I think 50 years ago would not have been forecast. But 60 years ago was the first paper that I know about that talked about doing congressional districting via integer programming. I highlighted the footnote now that this was actually presented at what was the predecessor of the OR Informs meeting, the TIMSS-ORSA fall meeting in October of 64. So this is building on a long-standing tradition that has been studied extensively in the intervening years. So what's the problem? What at a high level? That in some sense, fundamental to the US republic system is the notion that if I have a state, and I'm going to be focusing on a two-party view, but nothing that I'm saying is particularly specific for only two parties, that if I think about statewide, that there is a share for a given party VP of the votes for a given party P. The question is, how does that translate statewide to the number of seats WP? So what fraction VP gives rise to what fraction WP in terms of the outcome of the election? And if we think about a goal of a reasonable system of districting, one might want to have some notion of something like proportionality. Another element that is very much a part of the US system is some notion of compactness of a legislative district. And this comes from a historical view that representatives in representative democracy should reflect the local community. And so the compactness is one way of geographically viewing the extent to which you have a more unified, coherent community, rather than, in contrast to that, this so-called notion, which we'll talk about extensively, of gerrymandering, where you sort of think of these long filigree districts in terms of the shape of the districts. And indeed, these are in some sense competing metrics. If you look at the map on the left, and I won't give you a US geography quiz, but this is North Carolina. If you look at this map, if you look at a district like this, that's not compact. That's, again, this sort of long filigree kind of thing. However, in terms of, in some concrete sense, which I'll make precise later, this is proportional. And I'm using the usual convention of reflecting the Republican and Democratic parties by red and blue, respectively, and the intensity of the color reflects the fraction of the voting public within, as these borders give rise to particular congressional districts. Okay, so this map is proportional but not compact. This map is compact but not proportional. And to the eye, it's really the data underneath it that really gives rise to how we think about it. There's still a chair up front if you want to sit down. These aren't the, I guess I have to say relatively close. These aren't the only criteria that you might think about as being desired for a given districting plan for a state. One thing in this polarized society to think about is this sort of notion of a competitive district, that it should be possible for the seat to swing either way. And we might want to think about metrics that actually help capture, as I look at a proposed plan, some notion of competitiveness. And tied into many of these things, we might want some just sheer notion of responsiveness. If I end up getting a larger fraction of the votes, that should translate in some way to a larger fraction of the seats. You can think of that as responsive. And all these different criteria come in blending in terms of the kinds of issues that we might want in terms of a desired fair map. And of course, the competing element is, turn this so that the receiver is closer, is this notion of this political system gives rise for politicians to choose their voters rather than their voters to choose their politicians. and this notion of intentional gerrymandering, where the party who gets to draw the map can control the map for their own purposes. And so just take a look at this very stylized example. Imagine that we have 50 precincts being divided into 5 districts. Each precinct is either all blue or all red. The standard idiom is that on the one hand, the blue party might crack the minority red population as it does in that middle diagram and end up controlling all 5 of the districts with a majority of the vote. As opposed to if the red party got to determine the plan, it could pack all of the blue vote into those 2 right side districts and thereby actually control a majority of the districts, even though they were a minority population. So, and this is real, and to give you a sense of how real it is, we only can go back to North Carolina, which is roughly a 50-50 state. This is an old map when North Carolina had 13 representatives. It was 9-4 at the time. Now it's 14 seats and it's 10-4 in terms of the likely control of districts in North Carolina. Yes.
That else, like, by that, do you think that the people are kind of lying about statistics?
There's not, they're saying exactly what it means. It's just a question of, if I get to draw the district, I get to determine whether that district is majority red or majority blue. And as I take care of think about the geographic dispersion of where the population is, I get to control how that outcome occurs. And the stylized example gives exactly a good indication of how that control really can have definite impact. Okay, and I'm really pleased. Continue to ask questions that I'm happy to keep answering. I know that's behind a pillar. There is one seat in the middle there. It's yeah.
So we're talking about proportionality. Does it matter whether like people are actually happy with their own representatives, or if we were able to align the maps in such a way that like we just happen to get
So I am thinking about things in a statewide composite way, and I'll come to a precise model of what I mean by proportionality in a bit. But actually, that'll get pushed down quite a while. It'll come back. So that's one form that is very much in the news of what I'll call intentional gerrymandering. And there's another form that I would call natural gerrymandering. And this is exemplified by the state of Massachusetts. The state of Massachusetts, depending exactly which counting and which vote, has certainly more than 30% Republican vote, but maybe not more than 40% Republican vote statewide. But it's a very evenly dispersed minority. And so being able to draw district plans for 9 districts that actually have a Republican seat among them is already a stretch, even just one, even though, but they're a substantial minority, but it's very localized, and it's very therefore hard to exactly carve out a Republican district within a statewide map. So that's another phenomenon that I want you all to be aware of. So as I think about things algorithmically, we think about the state of Nebraska, that what I'm showing here is the map along with some atomic notion of a geographic partition. In this case, this is census blocks, and that we can think about that map as being represented as a graph where each node corresponds to each geographic unit, and any neighboring sharing a non-trivial boundary set of blocks are going to be connected by an edge. And in a very real sense, this is the natural representation from an algorithmic point of view of what we're going to look at in terms of the input. And in particular, I can think about sort of a formal algorithmic problem as being the map being given to us in terms of this adjacency graphs. Of course, the blocks themselves have non-equal populations, and so each node in the graph is an associated population. And I can also think about, and thinking about the shape of the district, it's important to bear in mind the geographic distance. Let's say, thinking about the node as being at the population center of gravity of a given node, of the distance between two adjacent blocks in terms of where their center of gravity is versus the next one, and thinking of that as encoded in terms of a distance. So that's one piece of the parameter. Another key parameter is, of course, how many districts are we going to get? As indicated by the map here, you see Nebraska gets 3 districts overall. And you might also then ask, and the Constitution says some things, the court has indicated each state has legislated their own view as to what the real rules are in terms of how population balanced districts should be. They must be population balanced for some view of the word, but I'm going to, in general, for the purpose of this really sort of more proof of concept level of work, take a relatively relaxed view. I'm going to take a sort of a 1% balanced view of district size. That's going to be a constraint. Districts, by and large, there are weirdnesses in various states under various things, should be contiguous. That is, it must be possible to traverse from any point in a district to any other point in that same district without leaving the boundaries of that district. And for some states, they actually require some notion of compactness, that well-shapedness overall. And again, there are lots of measures for how to think about this. There are many ways in which maps get evaluated, that maps get evaluated often in terms of how compact they are. And some use that as a proof that the map was drawn fairly because, hey, it just looks like a normal map. That's actually a bad measure in terms of that. And then we're going to think about various measures of how we can represent fairness overall. And this is really an interesting modeling question. Overall, what is it that we want to produce? In graphical terms, I want to partition the graph into k connected components. That if I think about contiguity, that translates into a connectedness constraint on each part. So I'm really computing a 3 partition of the underlying nodes of the graph. So algorithmically, that's the problem. I mean, of course, there are lots of things I haven't specified in real detail, but you know, understanding and recognizing this in a school of computer science, that this is a computational problem. This has an enormous literature, and they come into a variety of flavors. It's not just that paper of 60 years ago. There's been a number of works that are based in integer programming. There was a large piece of jurisprudence that gave rise to trying to understand distributional information across the set of all possible maps that are feasible, and a very beautiful, rich literature that developed MCMC, Markov chain Monte Carlo methods, for being able to generate these samples from this kind of a distribution. So this is a huge literature. These are a couple highlights, but really not really particularly focusing on one versus the other. I want to take a step back and give you a different integer programming formulation. In some sense, it's if we woke up today and didn't know anything in the past and actually just started writing an integer program, this might be in the view of how successful integer programming is, the sort of absolutely natural first formulation. So to highlight this formulation, I want to give you another stylized example. Imagine a state which has 32 blocks that are in that state, 4 districts, equally uniformly spread population. So each district should have 8 of those blocks. They have to be contiguous. So example, the yellow region is one such possible block, one such possible district that we might have. Now, one natural way to think about encoding that district is to think about a binary encoding with respect to blocks. I can just simply have a 0-1 vector that indicates, is this block in, is this block not in, and exactly in this linear strip going there, I have such a vector where again, as I go from 0 to 31, that I'm encoding the district that I just depicted overall in that figure. And so once I conceptualize things this way, the natural thing is, okay, encode all possible feasible districts. The beauty of math, we can think about it in a second and then cope with the consequences that follow. So let D1 through Dn be an enumeration of all possible feasible districts, okay? What do we then want to do? We can encode this in a sort of standard way as what is classically known as a set partitioning problem. I can think about an incidence matrix that I encode. Each row of that incidence matrix corresponds to one block. Each column corresponds to one potential district. And now I have this underlying ground set of blocks that have to be partitioned into exactly, if K districts should result into K parts, so that every block is covered exactly once. And we can write this out in the standard linear form. Don't worry about the math so much details, just understand the concept. And to do that, in fact, I'm going to depict this a little bit more explicitly. Here's a possible statewide map for the example I just gave you. And now if you look at it again, you can look at this collection. Suppose this was the complete enumeration of columns. If I look at any block and it goes, so any strip going across this way, there's one highlighted color that occurs at some point for every possible row. And so we're seeing that this represents the feasible solution that we see that it is on the left. Okay, so and of course we can encode this algebraically, if I point in the right direction. So we can think about the feasible space of all statewide maps is being encoded by, well, I have a decision variable which says for each feasible district, am I including that district or am I not including that district? And I'm going to need to choose exactly K of them. So K of them have to be, have to be ones, the rest are zeros. And I have to have this exact partitioning constraint, which we've just succinctly coded as this AX equals 1. And it's going to be some binary vector in Z2, 0, 1, to the however many columns I have. So now, sort of anticipating where I'm going next, I'm not going to enumerate all the columns. One standard methodology in integer programming is to do what's called column generation on the fly. That we start with a limited set of columns and that we, use our LP-based or linear programming-based technology to crank on that. And then when that seems to be not enough to get us a good solution, then we add more columns. I'm not going to do that. I wish I could do that. I don't know how to do that effectively. But what I'm going to do instead is I'm going to give you a heuristic way for generating, with randomization, a very rich set of columns that actually generate a robust, feasible set F. And the way I'm going to sort of think about how robust it is I'm going to be thinking about the ratio of the number of statewide plans to the number of columns. And what I want is something for which that ratio is high, that I'm going to try to exploit a notion of compositionality that allows me to actually have a broad set of statewide plans that's going to do this. And I'll show you concretely how this gets built. David.
Are you sort of implicitly assuming that the quality of a map can be evaluated as the sum of qualities of the individual districts?
Yes.
Otherwise, I think you'd get some nonlinear
Yes.
terms.
Yeah, I am going to, yes. The simple answer is yes. Good, but we'll talk about a variety of such metrics that come into play. Good. So this is, as I alluded to, is known as the set partitioning problem. There's nothing new at all that I had to say. The thing that I want to emphasize is that exponentiality in the number of columns in this setting doesn't scare us. Every time Amazon runs operations for a day, every time any airline runs operations for a time period, they're solving enormous set partitioning problems at one point or another overall, and doing it quickly and effectively, either to optimality or to near optimality. This is so the mere fact that we have an exponentially growing potential set of columns, that's not the impediment. The reason I'm not using sort of the standard technology of doing generation on the fly is that these columns are not as well behaved as what has come to bear in these other applications. I still believe that the right person can come along and do this right and actually solve the true problem. I'm just going to make do with solving a heuristically generated subproblem based on a limited generation of columns. So we have this sort of two-phase approach that first I'm going to take that not so visible map of North Carolina and use a randomized procedure to generate a partial enumeration of some number of columns, and then I'm going to optimize over that columns. And so, I'm going to need the column space to be good enough that it generates interesting solutions, but I better get that it also is small enough that I can then optimize overall. Question? Nope. Okay. Here in one slide is how I generate columns. So I'm going to think about things in a kind of recursive manner, in that at any stage of the recursion, I'm going to have a node in this tree that I'm building represent a region. So this node is representing that region. The root node is representing the entire state. And associated with each node is also an allocation of how many representatives that region should get. And now with randomization, I'm going to choose a number of children that correspond to partitioning that region and partitioning that allocation in a variety of ways, so as to generate new children that are going to continue on in this recursive way. So off of the root, you see I'm representing here 3 different replications. They have a range of how many different subregions they've been partitioned in, between 2 and 5. But there are 3 replicants, if you will, overall. And we're going to continue doing this process recursively until, for each node in the tree, it corresponds to a region that has 1 representative. And so once I get to that leaf node, then I'm going to stop the process overall across the entire frontier. So that's the overall schema. And really, if there are questions, please don't hesitate to ask. I'll give you a bit more detail a lot more detail about how we do this schema of actually at a base doing this partitioning, but that's the overall framework.
One representative does not one voter.
No, 1 representative. That is, so North Carolina at its root today has 14 representatives. So I would then also, not only am dividing the region, let's say here, into the western part and the eastern part as well, but I'm taking those 14 representatives, and because the western part is not as populous, it might go that I'm going to have to subtract 5 to the west and 9 to the east, and we'll have to do that in an intelligent way as well.
Is there some minimum size of population or size for a district?
The point is that it should be equal. The question, again, we need this population balance, and this is why I talked about this tolerance, that the computations that I'll ultimately show you will be based around a 1% threshold of allowing that much deviation, but that's going to be a constraint in terms of I may not deviate more than the average population. North Carolina has 14 million, I'm going to make it up, 14 million people, 14 districts. Every district should be within 1% of a million people in that district.
For instance, there will be some dead ends. Would there be some dead ends in this generation?
Yes, so if I might back myself into a corner and I don't know how to, but that's the beauty of randomization. You get out a new set of coins and you can keep generating. Good. Yes.
Yeah, that's right. This is perhaps related to the previous questions, but I just need some clarification on the number of subnodes that. Is this wrong?
It is, so it is actually process dependent. So, and one thing I could say is, so how many replicants do I generate? Typically, and this is again something that's engineered. I mean, this is not, theoretical analysis of algorithms. That this is a question of trying to understand the trade-offs of performance and what we're able to do. It's the kind of typical numbers that we use for runs are 5 replicants for each. So for each node, I'm generating 5 children. And I have a parameter that's sort of this fan out width. And then we also have this parameter of what am I doing for the size of the partition, into how many parts am I dividing? And that also is going to be a uniformly randomly selected number between 2 and 5 as well for most of the experiments I do. And this has gotten refined in a number of ways. So these are parameters that give rise to how the shape of the tree looks like, because of course, if I do into more parts in a given node, then it's going to reach only 1 representative left faster. That this will be a process dependent in terms of what the size is. Okay. Other questions? Cool. So why is this useful? So this picture really helps capture what's going on here. if you think about, now just take binary splits that I'm splitting into two parts. If you think about that top level being at this red line in this western half and the eastern half, as I think about all possible maps that I draw that I could possibly put together from there, and that's what you're seeing in the animation, is that anything that you might end up on the left fits together with anything that you might fit together on the right. And similarly, as you add these blue, let's say at the next level of partition, anything that works in each of those quadrants, each of those four parts, any little submap that I build in that one piece will fit together with the rest of the map. And so as you're getting a tree that's deeper, you end up with the number of possible maps growing exponentially in the depth of the tree. And this gives us a very rich feasible space in which what we're generating from the column space, doing it in this way. So a state like California with 52 districts is going to have a much deeper tree, is going to actually in many ways produce better solutions because of the expressivity of what we're generating. So I need to say a little bit about how I actually do a partition. And here I'm again going to use integer programming as my tool, and I'm also going to use randomization as a key element as how I build the integer program that I'm going to solve. So the high level view is, let's say I want to split North Carolina into 3 different regions, and they're going to end up having to be population balanced in terms of what we do relative to the number of representatives we allocate. Well, I want you to think about each of those 3 regions as sort of being centered, metaphorically more than anything else, at some one census block within the district, okay? And what I want to do first is choose a set of the set of the 3 centers before worrying about what those regions work. And I want, if I'm going to get 3 different regions, I want them to be dispersed. So what I'm going to do, and again, use the power of randomization, I'm going to choose the first center, in effect, uniformly at random, but not uniformly at random, proportionate to the population at random in that census block. So let's say that that's my choice of the 0th center. And now, in each subsequent iteration, I'm going to keep track of the product of the distance for each census block. I'm going to keep track of the product of the distance to all of the centers already selected and choose proportionate to that probability distribution. And that's going to be a forcing function to keep things dispersed overall. And so this might be the second, and the probability distribution then gets updated, and then I might choose this. Okay. So the color coding reflects there. So this gives us the centers of what I'm going to think about my 3 regions. And now I have to understand for those centers, how many representatives am I going to target? I'm going to do some standard KNN kind of partitioning. It's really not very important. And I might come up with a goal that says that those centers are going to be ascribed to that many representatives. Now, that's not the partition I'm going to use. Now I'm going to get out my sledgehammer, Garobi, and I'm going to produce an honest-to-God partition. And that's going to be done through the following integer. Oops, no signal.
Maybe the connection to your laptop?
The sharing, the sharing content change button color, and click share screen.
Yeah. I'm here on your door. I think maybe.
But I'm not here in Zoom. What we had before was that is shared content, and then this is what we got. Use Zoom up, use HDMI, plug HDMI, so maybe it's a question of the.
HDMI, yes. Maybe it's the connection.
I mean, I can try to switch to being in the Zoom. I know I have. No, that is technology.
It stopped sharing.
I was not in the Zoom. I was just using the. No, I didn't. I can't do that. Boom. There we go. Okay. Back in business. Yes, question.
Perhaps 3 slides ago. Could you
Why don't you ask the question, then I'll decide whether I want to show you the
One
business.
was the dash line.
Uh-huh.
So, I wonder how you think of that division.
I'm telling you how I'm coming up with the division. Okay, I mean, so I'm now showing you an algorithm to take one region and some number of centers and how to compute that partition.
And the second thing is that in previous 1 or 2 slides, I mean, by choosing the error, if you were to change your error that you choose, is that going to affect the results?
The whole point of this procedure is I'm going to do this multiple times, which gives me lots of different solutions that I'm going to be able to build back up together. So yes, it will definitely change it. And if I run the entire procedure from the top and I do this, and I'll show you results of it, I will get different results. And this will give me a portfolio of solutions that I can there. So let's go back to talking about how so I now start with a region. I tell you what are the centers, which blocks are at the centers of the different regions, and each of those regions comes with how many representatives it's supposed to be allocated as I do the partition of the current number of regions. And this integer programming formulation is what I'll call an assignment formulation. For each block in the census block, it's going to be assigned to one of those centers. So indeed, you see at that first constraint. But that I can solve by other means. That, as you see from, that may be just the usual initialization issue. Yeah, it's just the initialization issue. That if you look at that first constraints, the ones numbered 2, is that every tract is exactly assigned to one district. I need ultimately that the total population assigned to each center is balanced within this 1% tolerance. That's what constraints 3 and 4 give me. If I look at the other sort of tricky piece, maybe it's still not working, is that I need contiguity. So I need that if a given block is assigned to center I, what this constraint is saying is that one of the nodes closer to the center must, with respect to the graph distance, must also be assigned to I. And that's what that constraint gives me as well. So this gives me exactly what I want in terms of a feasible partition. What does the objective function do? This is a kind of standard dispersal trick. This is weighting the distance of how far you are from the center. And that helps make the partitions be compact, okay? And indeed, that parameter alpha is also going to be a random parameter, which is going to give us lots of leverage in terms of how we can produce multiple different solutions by solving under different sources of randomization, okay? So this is how I do partition.
It wouldn't be compact necessarily.
No, it would not. It is extra. I mean, in practice, it is compact, but you know, weird things can happen. Okay. Yes. And I think I'm just going to go back. Oh, there we go. So here's one run of back to North Carolina that just in the same yellow purple schema that I use for the size. And this is really on actual run of North Carolina. There are 2,200 census tracts or so in North Carolina. Each vertical strip corresponds to one potential column. Here we show 3 examples of districts that were drawn by this thing. And you see there's sort of this interesting structure that's based on the fact that we're doing this recursive thing that somehow these were all kept together at some higher level piece and gave rise to there. So you see that.
So why is this yellow color?
Those correspond, so each vertical strip corresponds to a 0, 1 vector. Yellow is 1, purple is 0. Okay. And I think okay, so finally, and I promise you I'd come back and start talking about proportionality. One way I can think about visualizing proportionality is that for a given election, there is some vote share between 0 and 1, and there is some seat share between 0 and 1. And so proportionality is, I want to be on this blue line, okay? Another measure of fairness that has received a lot of attention is the so-called efficiency gap, which has to do with wasted votes. And if I think about, again, the relationship between vote share and seat share, this says that the goal, the target is to be on that blue line rather than the original blue line. And we'll come and talk about that in a second in terms of what we might want to do in realizing it. But notice that these are both piecewise linear functions overall. Now, the next key element that I want to do is I want to use historical data to produce a model of a new election. And so what I'm going to think about historical data as giving rise to a probability distribution over what outcomes can look like. So if I look at this proposed district and I look at what the historical data is, I might want to use the results of how many votes for each precinct within that went red or blue over the last 5 elections and use that as a simple way of crudely estimating a Gaussian distribution. Okay, that there'll be some mean of red votes and some distribution that we get. So for example, at least in the mean, I'm saying that if I look at that district, that proposed district with probability 0.95, mean outcome that would actually give rise to a Republican majority. Okay. Okay, so one way that we now think about fairness, either with respect to proportionality or with respect to efficiency gap, is I take this probabilistic model and I say, under that probabilistic model for this map, as I think about statewide delineated, what's the expected seat share? Because given that I have now a map of a specification of these are the districts, I know a way of thinking about the probability that district is going to be Republican, and I therefore can compute the expected value as well. And that's exactly what I'm going to do, is I'm going to build this affiliation model where for each possible district, I have imputed normal distribution. And then I have an associated Bernoulli, which says that what's the probability given that normal distribution that in fact the seat share is more than 0.5. And then linearity of expectation is my friend. As I think about compositely, and this is really going after David's question, that I'm really viewing in aggregate the state as nothing more than the sum of what happens in each of those proposed districts. And taking advantage of the fact that I've built this underlying stochastic model, that I have an underlying expected value for the seat share. And while this was stated in terms of proportionality, and now that I'm making this precise of what is the expected statewide gap between the vote share and seat share across summed over all the districts that I select, there's nothing that the fact that it's proportional that I can take any piecewise linear function and map that as well and handle that as an alternative model. And then having done that, what am I interested in? In effect, the contribution to the expectation is just the gap for that proposed district. And now what I'm interested in is minimizing in my set partitioning formulation, I finally have an objective function, which is to minimize the expected value, the total value. The gap is a sign quantity. I can either be above the blue line or below the blue line, and I'm going to add that up over various things. What I care about is being at 0 in total. And so what am I interested in? I'm interested in minimizing the absolute value. Okay? So this gives us a formal model for how to, one particular way of thinking about fairness, and we can embed in that either the proportionality gap or thing. Now, the beauty of this formulation, limited as it is to just being sums, is that it's robustness to adding additional constraints. So for example, if I want to say, yes, the Supreme Court said Alabama should have 2 majority-minority districts, I can add that as a constraint because I have in my hand what are the potential districts. It's an offline computation of is that a majority-minority? I can just add that as a constraint to my formulation. And the range of different kinds of side constraints that can be adapted in this formulation is very robust, okay? But to answer your question, I run it many times, I may get many outcomes. So here are a number of runs that I have for North Carolina, and across the x-axis, I have the proportionality gap that was realized by the raws of my randomized procedure. And on my x-axis, I have some measure of compactness. What am I using as a measure of compactness? I'm just adding up the total perimeter of all the districts. That's one. There are a lot of measures of compactness. That's certainly one. And you can sort of see that as we do multiple runs, that there are, there's a full gamut of trade-offs with respect to which has proportionality gap. This solution up there was the one that minimized proportionality gap, really bringing it down, really to be dead on proportional, is not so compact. And you really, you can see all those squiggles in and out in terms of what we're getting. So, how compact it is. I actually showed some of these results to lawyers who were arguing cases at the state court level, and they say, oh, these are all very compact. But if you want something which, mitigates, loses a little bit in proportionality and gains you a little bit in proportion in compactness, here, the elbow of the trade-off curve, you can see a different map. But again, the main thing is the framework. Yes.
Which of the inputs, like you chosen an area and which is like red, let's say. But how about for some swing states and then we change color, everything and stuff for the inputs?
So, what I'm measuring overall is exactly sensitive to whether something is a swing state, that it is very much at the local level in terms of what we're seeing historically. North Carolina is one such swing state. And the question is, what kinds of maps can I draw for North Carolina in terms of trying to, in looking forward, produce maps that at the congressional level, deliver the kind of fairness that we're looking for. Now, one thing to stress, and I won't say this other than watching you having you watch through the zipping through the slides, is that the objective function I did in this absolute value is not linear. If I was given the tree structure, if I was optimizing something that is purely linear in terms of how I measure it, like how many majority-minority districts there are, I don't need integer programming to solve the set partitioning problem. The fact that I've got this tree structure decomposition means that I can do a standard from the bottom-up dynamic program and just try to optimize from that. So, and the visualized view is that, if the expected number of seats, if I were just trying to do something that was linear that I could just add up, then I would just try to maximize as I go up the tree. So there are settings such as in optimizing majority-minority districts in expectation that we might do this. And we can do this across all the 50 states. Well, only 43 because 7 are only one congressman, and so that's not very interesting. David.
So you said that your goal is to provide like the tools and the formulation and the framework for people to reason about this. And specific objective function can be swapped out, which means it can be swapped out for maximize the number of seats that my party gets when my party is in power at the state level. And you've just built a tool that makes it really nice to produce
Guilty as charged.
compact-looking districts while still maximizing.
So what this plot shows, and if you, it's not a whisker plot, that you see at the end of those bars. Indeed, maximizing and minimizing isn't even that integer program. It's the dynamic program that I want. And you can see the range of what the solutions that we're generating actually give rise to overall. So yes, I built a tool and, I have to live with its consequences, but I'm going to work with folks that I think are, that fortunately, and unfortunately, there are a lot of subtleties that I'm not showing how to do And by being able to control the technology, I also can control its application, hopefully only for good, not for detriment. But to make that point clear, as you just said, I'm building, very compact looking maps. And if you look at the nationwide swing between what the most every state optimized Democrat versus every state optimized Republican, that itself generates a 20% swing in the number of seats. I mean, and you think about, relative to there, we're currently talking about a Congress which has got a gap of like 8 maybe. And, this is instead a gap of like 80 that's simply in terms of how you draw the maps collectively. And they look real. It's not these sort of flaky looking, odd maps. They look real. Okay. Good or not good. That competitiveness can range enormously. That if I think about, having some formal notion of the expected number of, the probability of there being a seat swap in terms of changing party, some maps are just as bad as we currently live through, that there are a very, very small number of competitive districts, but one actually could engineer a much larger number of competitive districts if that were our goal, and thinking about the overall ensemble. Kind of depressingly, although I showed you in North Carolina, you were able to absolutely hit on proportionality, but there are a lot of states where at least, exactly depends on what does it mean to absolutely hit on proportionality. There are very few states that it is as easy as North Carolina. And that gives rise, and I want to, in the last 10 minutes, give you a hint of 2 other pieces of work that are going on. One is relation to this bill, which died in the well of Congress in the session before last, which proposed an entirely different mechanism that Congress could adjust the way in which elections are run. So New York has 27 districts. Rather than having 27 single member districts, imagine a state in which you only have 9 districts, but each district elects 3 representatives. So one question is, well, how do you choose 3 representatives? And what we're going to show is an analysis of the characteristics of this bill using the optimization infrastructure and I'll give away the punchline right off the top because short on time, that the end result is that under the right implementation of this bill, 2 things can happen. One, you can generate maps for which the likely outcomes can be much more proportional to that in terms of if a fair-minded independent party were trying to build a map. That's consequence 1, something which we fell short of in terms of what happened in the single member districts. And 2, a partisan-oriented, unfairness-minded party is greatly limited on the extent to which you can bias the outcome. Rather than having that 20% gap between the most expected seats for one party than the other, it gets narrowed by about a factor of 3 by considering this. And so the tools that we did provide us a means for analyzing this piece of legislation, which, while underspecified, is something that I strongly support. So that's sort of the punchline. Let me sort of talk a little bit about mechanism design to do this. How do we choose 3 representatives from a district? Well, here's a bad way to do it. It's winner take all. Everyone gets to, we're choosing 3 representatives. Everyone gets to vote, and the top 3 vote getters wins. That's in effect what we do for the Senate, albeit not synchronized. And we all have seen that does not give any minority representation, that it's basically 2-0 for almost all the states in the union. Here's a much better mechanism, single transferable vote. And the point I should have highlighted in the bill is that the input to the vote is now a ranked choice ballot. Okay, so many of you may have understood how ranked choice votes work when you're electing one person. Ranked choice when you're electing one person is sort of an iterative scheme where in each iteration you check, does somebody have a majority of the vote? If not, take the lowest vote getter. look at all of their lists and go to the next person on that list and iterate until somebody does have a majority of the vote in terms of the current favorite. And of course, one thing we know that seems overly vacuous is that, of course, only one person can get a majority of the vote. What if I want to elect 3 people? Well, now I claim that the natural thing to think about is getting more than a quarter of the vote, because only 3 people can get more than a quarter of the vote. What's an inherent issue to think about is you don't want people to gamify what they do in their votes and say, well, I'm not going to rank this person because it's certainly going to get a quarter. Let me instead, vote for other people and help boost their totals. So what you want to do is take away the power to sort of waste your vote. And the way you do this is this single transferable notion that, look at round 1, Armando has 27.2% of the vote. Armando has 2.2% more than they need to be locked in as one of the top 3. So what we're going to do is take 2.2% of the vote and actually also redistribute that to those voters' next choice. But it's 2.2% out of 27.2%. Which voters do we choose? We'll do it fractionally. We'll proportionally choose according to how the rate in which the second place votes go and redistribute that way. So we have 2 redistribution rules, both like in the second round where no one new has more than a quarter, and we eliminate Dune, and we iterate this way until we have 3 people that have more than a quarter of the vote, okay? So this gives us a very robust, truthful, incentivizing system, well studied. This is not new to us. And one thing that's known is that this is very minority voice respecting. And this gives rise to a mechanism that ensures, as I indicated, the sort of two-sided gains that, in fact, even with just thinking about 3-member districts, even 2-member districts, but that's bad, those are dangerous from another point of view, you end up inhibiting partisan gerrymandering and enhancing the ability to get proportional voting. I'm running out of time, so I won't go through the plots. I want to talk about, for 1 second, one other piece of work that one can ask. Suppose I wanted to optimize majority-minority districts. Can I just use the same machinery? Well, in some sense, the simple answer is yes. I just run it, and just as I said, I change my objective function rather than adding minimizing the proportionality gap. I could just maximize the number of majority-minority districts. That doesn't actually work so well, but a few tweaks to the overall structure allows this, that when I think about the last level of partitioning, at that last level, I can say, okay, don't just care about compactness, care about getting majority-minority districts. And just doing that in and of itself allows us to really outperform a number of standardly considered other randomized methods. And this also allows us to do things like a local search, that I can take a current map and look at, here's a region of 5 or fewer districts, and use that to redistribute districts in that small region, maintaining compactness, but still maximizing the number of majority majority. And this allows us to actually produce things. So the meta message that I want to give with this is that although I've given you this framework, it can be adapted for a number of purposes that gives us tremendous power in terms of how integer programming methods can be used. And I think I'll just try to leave this here. Skip ahead just to my final map to show you. Oops, that's one slide too many. No, I won't. Go back to the start. That I was going to show you a map of Texas on the multi-member districts, but I hope I've given you a sense of the power of these tools and the sense of different kinds of questions and the role that they can play in analyzing prospective legislation that allows you to understand that we actually have some degree of control and we can actually influence in a way that allows policymakers to understand better the kinds of maps that are potential and the kinds of maps that aren't. And for that, I'm happy to take more questions.
The floor is open for questions. Just make sure to speak up.
Michelle,
So I think I may have lost this along the way. In contrast to like traditional column generation, I guess in traditional column generation, you don't want to generate all the columns up front because it's a huge memory footprint. How are we getting around this here, or is it just modern computers' memory is cheap?
I'm not generating, I mean, we're getting around it because I'm being very careful in how I'm generating that initial set. And that I'm generating an expressive set
That's not too big.
that's not too big, and I'm doing it fast, and so I can do it many times. So for example, one benchmark of sort of, you can ask, well, how well are you doing? And you know, it's heuristic and there. So the competing technology for generating ensembles of maps is this MCMC driven way. Our max min range is far bigger than what MCMC techniques deliver in terms of the range of solutions. So that to me is suggestive that with respect to any reasonable objective, that it is a mechanism that because we're building, or and it's again limited by the fact that we're thinking about metrics that are composite and additive statewide, that across the full range of those objectives, this is a mechanism is actually generating there. It's not perfect, and it's, there's this sort of tuning aspect that I did for majority minority districts there, but the point is we have the flexibility to understand what the objectives are and how to tune so as to be able to go that way. Ideally, I'd love to be able to do things over the full column space. I just don't know how to do that effectively.
And then just the intuition again for why this outperforms something like Recom or MCMC is this cute thing with the tree that I can fix what I did over here and combine it with any choice of stuff that I did on this to the tree. So there's a lot of rich cross mingling.
Yeah. Yep, exactly. You had a question before, Andres.
Yes. How long does the set partitioning formulation take versus the dynamic programming if it were different?
I can say a stupid answer, which is longer. It's actually so it depends, of course, am I doing things at a census tract level, or am I doing it at a precinct level, or am I doing it at a census block level? If I want to do something at a census block level, I damn well better do I'm going to use dynamic programming whenever I can. At the census block level, that's beyond what Gurobi can cope with currently. Reasonably, I mean, there are various tricks that are still being tried. There isn't a particular need to do it at the census block level because, among other things, votes are at the precinct level. And so it's really the projection of what you can actually adapt from the block level to the precinct level. We've mostly done all of these work has been at the census tract level, which is actually where most people who are doing the competing technologies are actually doing that on. At that point, the set partitioning problem isn't the resource hog, it's those partitioning IPs. That's the resource hog in building the tree. So for example, in the maps I didn't really show you on Louisiana on majority minority, that was the limiting factor. We only did 2 or 3 replications and we only did binary and ternary splits. And that helped control the size of the tree, and that was because we didn't want to spend too much on the partitioning IPs. And of course, 5-way partitioning IPs are a lot harder to solve, and it's not accidental that I stopped at 5. 6 is much harder than 5 in terms of how those IPs behave overall.
How much of that impact do you think this tool is going to?
It's a work in progress. I view this as a 10-year project that I'm working to sort of provide interaction and support for a variety of people who are on the ground in different roles. While there's still some court case of Florida is currently under a new round of court cases, and I'm trying to prepare myself to inject into that discussion. Really, the next time things gear up will be in 2030, this is the long-term timetable, and I'm trying to build up a robust and rich enough ground working so that we can be relevant in the right scenarios where the contentiousness will arise. And it will. We just know this, that's going to be a fact of life. David.
You mentioned that like five-way partitioning is much more of a resource hog than two-way partitioning. Given that you're doing recursive partitioning, in principle, you could get your five-way partition after doing multiple two-way partitions. So what's the benefit of doing the multi-piece partitions directly rather than repeated binary partitions and just more levels in the tree?
So it's not so important lower in the tree. It is important higher in the tree. We get much more diversity in the kinds of maps that result by how we doing the having different ways of partitioning overall. I mean, it really comes from a kludge that we don't really understand what we're doing, but we're able to see the impact overall. I don't have a good answer. I just, I know it because I see it kind of thing. I don't have a good explanation, really. That's sort of the honest truth. Yeah.
How much national government intervention do you think is going to be required before some of these battleground states shift to using more of this analytical approach for this?
I don't think the national government will play a role at all. I actually think that, in particular, one of the unfortunate things, from my perspective, is that the Supreme Court basically washed its hands of partisan gerrymandering. That's just fine. Party has control, they can draw the map that they're. What hasn't been abrogated is race discriminatory districting. And now we get to a really nasty, subtle thing, is that what isn't clear in terms of current jurisprudence is whether you have to prove that it's discriminatory from a race perspective beyond what would have been a consequence of partisan perspective. So if you happen to have done a very partisan bias swap map and one of the consequences of that was racially discriminatory, it is currently conceivable that the court can say that's completely fine. It's kind of ambiguous under current decisions. More likely that they would say that is completely fine. So what's happening in contrast to that is that states are now mounting movements to change local law and local state constitutions to enforce that. So my own state, New York, went to a very typical New York set of politics in that in 2010, the districting plan was controlled by actually the Republicans, even though the Democrats controlled the assembly and the governorship. But there was this cabal of 4 Democrats that voted with the Republicans in the state Senate, and as a result, they called all the shots. And one result for that is when the Democrats regained control of all branches of government, they rewrote the Constitution and rewrote the law that said, here are various fairness principles that districting should abide by, and here is a so-called independent commission that's going to set up the rules. Now, it was not independent, it was just exactly party balanced commission. Part of the reason we're on map 4 is that the independent commission drew up a map. It was not as democratic favoring as the democratically controlled government was due, and the legislature tore up the map that was proposed by the independent commission. But that was then overturned by the courts because the new map that the Democrats put into place wasn't aligned with the state constitution. Because the state constitution very clearly aligned, that partisan gerrymandering was not okay in very concrete terms. So this is going to happen much more at the state level than at the national level, I think, in the near term.
Thank you.
Yeah, last question, because we are way over time. I guess we have the room for another half hour. So.
And I'm happy to stay after, come up and ask questions afterwards.
Okay, so it looks like you've got a collection of tools that create nice maps. Is it possible to solve the inverse problem where given a map by one party or the other, you can say that like this map is fair, this map is unfair?
I mean, the only thing we can do is just sort of demonstrate the range of metrics. And that I think is one of the most important thing that analytics can do is to produce exactly that kind of detailed analysis that's transparent. I mean, I think that one thing that isn't out there yet is a voter-facing set of tools that allow, I mean, there's nothing in here that couldn't be converted into a good UI that individuals could play with on their own and understand the impact of. All of the data is public. I mean, as much as, voting data precinct by precinct, that's part of the public record. So everything that could be done in an era of transparency is really where I think, though, and in fact, one of the things that I'm looking to hopefully do in the expense of it is to find a partner on the UI front, because in order to make a tool like this really effective, you want the policymaker to be able to add weird side constraints that we can anticipate and have that fed back into the model in a way that, yes, we need to re-optimize it, but we're not going to split this census block from that census block, or a range of other kinds of things. And this is the sort of thing where we have the technology to do this in a really holistic way to bring the capabilities, not just at this crude level, but at a fine grained, really, on the ground, fighting the real battles kind of level.
I think we need to wrap up, but David's going to stay so you can come up and ask him questions. Thank you so much, David.